We should now turn to the first talk of the afternoon, which is from Jo Carpenter. Second time we've heard from Jo, and we've been looking at her title, so I'll just leave it to her.
Thank you,
Thanks, Jo.
John. Thank you. Yeah, so I'm going to be talking about ship rat population dynamics across an elevational gradient through the 2019 megamast. And I'd just like to first thank, in particular, Dr. Tiano for their support of this work, and in particular the contractors and technicians that were out on the ground collecting all these data. It was a huge effort, so thank you so much, everyone. So across New Zealand, as we've kind of discussed a little bit already, we know from tracking tunnel data that ship rats seem to have different population dynamics across different habitat types. And there's this general pattern for ship rats to be more at consistently high levels in warmer, richer, more floristically diverse forests, whereas in cold, high elevation, maybe floristically simple forests, we tend to have far fewer ship rats most of the time, but then they can briefly become quite abundant in these forests, generally in response to masting. And elevational gradients are a classic example of this. You know, you might have a valley floor that is warmer, that has a high diversity of different plant species, more invertebrates, and you might have a consistently ratty population there. But as you go upwards and you end up on the edge of the tree line, perhaps, where it might be pure beech forest, less invertebrates, you might only occasionally detect rats in these kind of habitats. And on a national scale, this is shown really beautifully by this figure from Susan and co-authors 2019 paper. In this figure, you can see the pink and the red colours represent consistently ratty forests, and the green and the yellow represent these more eruptive rat forests that don't record rats very often, but when they do, they're quite abundant. So what is limiting ship rats from being more consistently abundant in the cold forests? It could be direct temperature limitation. So like John said earlier, our ship rats in New Zealand have originated from southern India. They're not exactly cold adapted. So there's the potential that they just can't survive these kind of temperatures that can occur up in these forests. Perhaps they don't have enough warm, dry denning sites. Perhaps they don't breed when they get really cold. Or there could be some kind of mechanism like juvenile survival is really low. The alternative explanation is that it's food limitation. Like I said, these forests tend to have not many plant species, and there are fewer invertebrates. So it could just be this direct effect of not enough food to sustain rats all the time. Of course, food limitation is an indirect effect of temperature. These forests are not very resource rich because they're cold. But what we do know is that in beech mast years, rats often become abundant even in these cold, high elevation forests. And that's shown really well in this graph from Jenny Christie and co-authors 2017 paper, which shows the number of rats caught in traps along an elevational gradient on the x-axis at Mount Misery and Nelson Lakes. And you can see that in the beech seed years, we suddenly start detecting rats at 1,000 meters at high elevation, whereas in a non-beech seed year, you don't trap rats at this elevation. So what's the mechanism behind this sudden change? It could be that rats always live in these cold, high elevation forests, but just at incredibly low densities. And then when they get this flush of resource in a mast, they can suddenly breed and become detectable. Alternatively, in a mast year, there could be this upwelling of rats from the valley floor where we suddenly start detecting them up high. We don't know which of these mechanisms is occurring because all our data really come from tracking tunnel data or trapping data, and that doesn't give the right kind of insight into what's driving this pattern. But the answer will really suggest whether it's cold or food that's limiting rats from normally occurring in these forests. And if we can unravel the mystery of when, why, and how rats appear in these high elevation forests, we can get this understanding of what factors are normally keeping them out of these forests and how that might change in future. So our aim with this study was to develop a mechanistic understanding of how cold temperatures and food availability limit shiprat abundance. And the way we wanted to do that is we wanted to utilize this incredible natural experiment that occurs in a beach mast year. The landscape is suddenly flooded with food. So it's the perfect kind of experimental setup really to test this kind of question. So what we wanted to do was measure rat density during a beach mast across an elevational gradient. We wanted to feed rats at high elevation to see if we could maintain their high elevation populations once the mast resource had ran out, if we kept giving them food. We wanted to understand how these rats got to be in the high elevation forest in the first place. Was it this upwelling of rats from down lower, or was it in situ breeding from very low density populations? And finally, we wanted to know what happens to these rats in high elevation forests once the mast finishes. Do they die up there, or do they go down slope? So where do you go to answer these questions? Obviously, you go here. The lake to the right is Lake Alabaster, and the river running through the picture is the Hollyford River. So we're in southwest Fiordland, or northwest Fiordland. And what you can see is there's a fantastic elevational gradient present at this site. So the valley floor is almost at sea level, and then the tree line is at about 1,000 meters. This valley floor is more complex. It's a mixed beech podocarp forest, and it's obviously warmer and just more structurally complex. At mid-elevation, you've still got quite complex forests, and it's quite warm there too. It's kind of a mixed kamahi beech forest with some rata and totara. And then finally, at high elevation, this is very simple silver beech forest predominantly with not a lot else going on. So it represents a fantastic gradient of these kind of conditions that we want to understand. So we set up the study in July 2019, which was the year that we had this mega beach mast year, and we carried out the study until January 2021. We measured shiprat density across the elevational gradient using capture mark recapture, and we also snap-tracked rats across the elevational gradient to look at their breeding demographics. We provided supplementary food on 2 of these capture mark recapture grids, the kind of mustard coloured ones, once the beach mast resource had finished. And we also measured stoats through cameras and food availability along the gradient. We also radio collared almost 40 shiprats at high elevation and tracked them every 2 months to understand where they go once that beach seed runs out. So 18 months go by, we tagged 797 shiprats, we snap-trapped and necropsied 379 shiprats, and there's probably at least 2 people that never want to go on a field trip with me again because of the state of our accommodation. But we got some really great results out of everyone's occasional pain and discomfort. So in this graph, we're looking at shiprat density through time. On the y-axis, we have rats per hectare. On the x-axis, we have time. This beech tree is representing when the main seed fall occurred in the autumn of 2019. So we got in there in the winter, and rats were already at high densities at both low and mid elevations. At mid elevation, rats were at 17 rats per hectare. And these are some of the highest densities we've ever recorded on the New Zealand mainland. But it's worth noting that we have very, very few measures of shiprat density in a beech seed system during a mast year. So potentially this is quite a normal result. We just don't normally do density estimation. It was a different story at high elevation, however. We only caught 2 individual rats at high elevation, and they obviously weren't very abundant at all. But things had changed by the time we came back in the spring, 3 months later. So by then we had rats at about 6 rats per hectare at high elevation. And then pretty much all the populations kind of either kept stable or increased right up until that summer post-mast, the summer of 2020. And after that peaking period, they all declined quite rapidly until they reached almost zero density by February 2021. We were only really detecting rats on the low and the mid-grid by this time. So we can also use these same data to look at the survival and recruitment of the ship rats. So in this first graph up the top, we have the per capita recruitment rate for these rats across the elevation. What you can see, so this is 3 monthly per capita recruitment rate, there's this initial big flush of recruitment happening at high elevation, which is not surprising because we know the rats need to go from almost zero density right up to 5 per hectare. So that's occurring, and there's also some increase happening at low and mid elevation. There's a little bit of recruitment that keeps happening kind of right up until the summer, but pretty much as soon as you hit 2020, there's no more recruitment happening for these populations, regardless of your elevation. And this is something that's mirrored in our snap-trapped rats. We didn't catch a single pregnant female in 2020. So it seems they really shut down their breeding after that mast resource runs out. We've got 3 monthly survival down here on the bottom graph. And again, this is a similar story. Sorry, I should have said these dotted lines across here represent when beech seed germinates or rots. So survival's initially quite high across all elevations, but pretty much from that summer onwards, it declines rapidly and hits a real pit around the spring of 2020. So what effect did our supplementary feeding have? Remember, we wanted to test whether we could maintain ship rat densities at high elevation if we kept feeding them once the beech seed ran out. So in this graph, this shaded area represents when beech seed is available. And we started feeding rats pretty much at the edge of it in January 2020. We initially had quite a good result. We improved the survival and recruitment of our fed rats compared to our non-fed rats at high elevation, which is the red marks, compared to our dark blue fed data points. And in the winter, although our fed rats had also declined, we still managed to maintain significantly higher densities of rats compared to not fed rats. But, oops, by the spring, they both fed and non-fed rats had essentially declined to non-detectable levels again. So we made a bit of an impact with our feeding, we sustained them for longer, but really we were just slowing the rate of the crash. What about our radio-collared rats? Because we wanted to know whether rats at high elevation died in situ in these forests or whether they actually ended up going down slope to more favourable habitats once the beech seed ran out. We ended up with 34 collared individuals because some of them slipped their collars. And we had quite high mortality with these rats, even though we tracked them a few days after collaring and they were fine. It still seemed like a decent proportion of them died within 2 months of being collared. But it's important to remember that survival was really low overall for all rats, regardless of being collared at this time of year. So this could be quite normal. The take-home message, though, is that the rats did not move down slope. They all died in situ in this high elevation forest. So what caused the crash that occurred across all populations of the rats at the study site? There's a few different factors that could be at play here. The first is food limitation, or it could be cold temperatures, cold winter temperatures specifically. And finally, there's predation pressure from stoats. So if we start with food limitation, and just looking at this familiar graph again, like I said before, our beech seed germinates and rots around January 2020, and it's only shortly after that that we start seeing this significant decline across our populations. So the timing's quite consistent with food running out. We also know from our necropsied rats that their body condition was lower in 2020 compared to 2019, which is also suggestive of food limitation. And what often happens when rats or any rodent overshoots their peak of the regular carrying capacity of a habitat is that these really strong density dependent mechanisms kick in and the rats stop breeding and stop recruiting. And this is something that seemed to really happen at the site. So like I said, we didn't get any pregnant rats in 2020. Just looks like they completely shut down that recruitment because they had so overshot the regular resource that's available in these habitats. But if food limitation was the sole reason of the decline, we'd think that our fed rats shouldn't have declined to pretty much zero. So obviously something else was going on other than food limitation as well. What about cold temperatures? Well, again, the decline really starts post-summer, and that's probably a little bit early to be really related to mass mortality happening due to snowfall or cold winter temperatures. So it seems like cold temperatures weren't an immediate factor driving the decline. How about stoats? Here we have our same rat density graph on the top, but down the bottom we are showing the mean stoat detections per 1,000 camera hours across the site. And what you'll notice is in this period, which is when our ship rats were in their increase phase, this is when stoats were barely detectable. But by the time we hit our rat decline, that's when we start recording significantly more stoats. And this is because stoats, their response to all this increased resource in the system, all these rats and rodents that are now there, their response lags quite considerably because of their breeding biology. So it's only until the summer after the mast that they can have this really successful breeding year. There's all these kits that are suddenly out rushing around looking for food, and that's what we're detecting here in this March camera round. We're suddenly seeing all these extra stoats in the system. So the timing of that increased number of predators in these forests really does correlate with when our rats start to decline. And we did find with our collaring that 20% of our collared rats at high elevation ended up dead in stoat dens. Although it's important to note that this could be related to stoats scavenging rats that were already dead rather than stoats killing the rats, but it's still reasonably considerable. We know that theoretically stoats can never stop or suppress a rodent eruption because their rate of increase is a lot slower than the rodents. So the rodents always get ahead of them first. But we do know that theoretically stoats should be able to hasten the decline of a rodent eruption. And potentially that's what we observed here. So to bring all these factors together into one graph, what we get is a fantastic breeding year for the rats initially in response to the beech seed fall. They reach these really high densities just as the beech seed starts to germinate and run out. And so they've massively shot through the ceiling of the regular carrying capacity of these sites, and probably density dependent mechanisms kick in which stop them breeding and recruiting. This is something we see with rodents in Europe in response to mast events as well. They often get such strong density dependent effects that they actually end up declining to below their normal carrying capacity in the site. So they decline past the usual density that they'd be in a non-mast year. And that could have happened to Alabaster too, given how low their densities were at the end of the study. Stoats also suddenly increase in the system around this time, around late summer of 2020, and they could potentially be hastening this decline of ship rats in the system. So in summary, ship rats reached very high densities at the site, but the densities that we recorded at high elevation lagged behind increases at low and mid elevation, and they were smaller in magnitude. Potentially this is because it could have been driven by immigration and the rats didn't have enough time to reach high densities before beach seed ran out, but we'll hear more about this from Dean shortly. Almost all breeding ceased in the year post-mast, and this seems suggestive of a density-dependent effect in relation to food limitation. There's also potentially a role for stoat predation, hastening that crash of ship rats at the site. When we fed our rats at high elevation after the beach seed had ran out, we managed to slow their rate of decline and we maintained a reasonable density of rats over the winter, but they still crashed in the spring. And what this all suggests is that the direct impacts of temperature on rats might be trumped by effects of baseline food availability. So basically, this seems to suggest that if you give rats enough food, they can cope with these really inclement, nasty winter temperatures. But of course, baseline food availability is also related to temperature itself. Thank you very much. Are there any questions?
Thanks, Joe. It's cool, very punctual. There's indeed one question already from Elaine Murphy. What did you supplementary feed the rats? She says, I found quality of food was really important when I supplementary fed mice.
Yes, I read, I think it was from your PhD, wasn't it, Elaine? I definitely read that, and it was very helpful for us thinking about what to feed the rats. We ended up feeding them sheep pellets, and that was because the sheep pellets had a very similar nutritional composition to commercial rodent pellets. So we figured it was probably the best. It had all the right balance of nutrients for them.
What did you stick it in? A corollary question. I mean, how did you distribute the food? Was it in bait stations?
It was in bait stations laid out across the grid because we wanted to prevent possums getting into it, basically. And we ended up feeding them every 2 months. We'd refill the bait station. So we just wanted to make sure that the food stayed dry and available for them throughout that period.
A related question from Doug. Do you know how the amount of supplementary food, e.g. kilojoules per hectare, compared to the beach forest, the beach mast?
Oh, that's a really good question, Doug. I am not sure. I'd have to do the equations. Beach seed, I guess especially silver beach seed, which is quite small. I don't want to hazard a guess, actually. I'll do the equations and I'll get back to you. But I imagine it's similar, but I still feel like we probably didn't feed our rats enough. I think we might have got a slightly different result if we'd been able to give them more food.
A query from Robert. Joe, is there a reason why no data gathering on rat density occurred in April 2020?
April 2020. Yeah, so we tried to measure density every 3 months. So it was seasonal. So we'd do a summer round and an autumn round. And for sure, the density estimation should have happened in April, but this is when we got COVID and we all went into lockdown. So yeah, very sharp eyes there, Robert. It was a little bit delayed that year, but we got in, which is good, eventually.
And from Reese, what did mice do over the time, Joe? Not enough time, for the slides, but what did mice do?
Yeah, that's a great question, Reese. The mice just showed their usual typical inverse relationship with the rats. So we didn't really record many mice in our tracking tunnels at low and mid elevation. We recorded more at high elevation. The mice detections diminished when our rats increased at high elevation. Yeah, mice were there. They were definitely responding, and we caught them in the live traps quite frequently as well. So they were definitely reasonably abundant, I think. But it was hard to say whether there were more mice somewhere than anywhere else because they were so affected, I think, by that behavioural response to the rats.
You've got data though, Joe, certainly from tracking tunnels for mice.
Yeah, I guess we've got the tracking tunnel data and we have live capture data as well. I mean, not density, but number of mice that we just catch in the live traps.
And just a follow-up question about the sup food. Was it available over the entire 2 months between refills, or were the bait stations empty when you went back to refill them?
It was a mix. So sometimes they were empty, especially when we had the issue with the lockdown, because obviously that affected our feeding regime as well. So I think by the time we went back in there to refill, they were definitely empty then. But at other times, like later in 2020, they were still full quite often, or not full, but some were full. They were at quite dense spacing, which I think helped a little bit.
And a final question before Dean. Joe, it's notable on your chart that rat density at low and mid altitude did not seem to increase during spring 2019, but they were still breeding, I think you said. Is your conclusion that these lower tiers were a source of young rats, explaining the rapid growth in the upper tier?
I think that is part of it. Yeah, I think by the spring of the mast year, they were starting, Dean will definitely talk about this, but they were starting to more reach the carrying capacity of those sites. So there was this export of individuals happening. Yeah, no, I think that's definitely part of what we're seeing.
Okay, thank you very much. And thanks everyone for questions. There are more questions there, we know, and we'll pick those up at the beginning of the next session.